calculus students, we are doing example video for 2.3b in blue, 2.3c in purple. We're going to be going to look at some different things today. This is going to take a little bit. Make sure you watch the whole video. Make sure you take good notes. Here we go. 2.3b. Number 56 is an example, and I put please see computer screen. So what your book says for number 56, use a computer algebra system to differentiate the function. Let's come on over here to the computer screen. The program I usually use is Wolfram Alpha that you can see up here, .com. And all I did is I typed right in here, derivative of, and that very complicated expression. And you can be really liberal with how you word it. You could have used derivative symbols, but you can simply type the derivative of and very carefully using parentheses. And when I hit enter, there we go. Look at that. Wolfram Alpha does that for you. Gives you the solution. It also graphs it, gives alternate solutions. Super cool. Right, so that's what you do in this section. Number 66, we're going to be looking at the calculator. Let's see what they're asking for. On number 66, it says find the equation of the tangent line to the graph of f at the given point. I just realized that I should have actually written that too, because part of it is calculator. So that's okay, right here in black. And then I'm going to go ahead and erase it. I'm going to write number 66. And they want the equation of the tangent line. You know automatically that you stop and write the equation of the tangent line. F of c plus the derivative of f at c times x minus c. And what's given to you here is the point 2 1/3. First of all, we're going to pop that in. The 2 goes here. The 2 goes here. The 1/3 goes here. There we go. Now all we need is the derivative of f at 2. So the function that they actually gave you is x minus 1 divided by x plus 1. Let me check and make sure I wrote that right. I did. So we need to take the derivative of this function, evaluate it at 2. So let's go ahead and use the quotient rule here. I'm going to talk my way through it. Here's f, numerator, g, denominator, talking it through. I take the derivative of f times g minus, I keep my f and multiply it by the derivative of g all over g squared. Now, at this point here, what you could do is clean this up. Notice the numerator does clean up quite a bit. I wouldn't clean this up too much though, because we're going to be popping a 2 in, and so that we should do that as quick as we can. But let's take a look here. Notice that I have a positive x and a negative x, which cancels, a positive 1 and another positive 1 minus a negative 1. So I have 2 over x plus 1 squared. And we are going to evaluate that at 2. They said x equals 2. So let's take a look. That would be a 2. This would be a 3 squared, 2/9. There we go. There's the equation of the tangent line that they asked us for. Just wanted to show you how to use n derivative. Again, to get the 2/9, let's go over. I'm going to grab the calculator. Let's go over here. Notice on the calculator, I actually put the function in already, x minus 1, x plus 1, into a y1. So I'm just going to get out of that screen. I'm going to hit my math button, go down to n derivative, and my variable I'm using is an x. At this point right here, I could retype the function in, but I already put it in a y1. So I'm going to hit variables, y variables, it's a function. There we go. I'm just going to put y1 in, and I wanted that at an x value of 2. There we go. When you hit your button, it gives you a decimal, and let's see if it will switch that to a fraction for us. It doesn't, but it 0.222222 is actually 2/9. There we go. So our calculator can do the end derivative for us. I am going to erase.
And it's 28-10, Tampa Bay over Green Bay. That's awesome. Okay.
There we go. Let's keep rolling. Little sports break there.
Yeah, a little sports break.
Little sports break. Number 75. Find points at which this function has a horizontal tangent line. I need you to, when you see those three words, horizontal tangent line, I need you to relate that to what math you have to do. Horizontal tangent line, they are talking about the slope, which is 0, of a tangent line, which hits a curve at one point. They're talking about the slope at one point, that is a derivative. Because it's horizontal, they want to know where the derivative is 0. That's the math we're going to do. We want to know where the derivative is 0. Let's go ahead and take the derivative of this function. I'm going to talk my way through the quotient rule, f and g. The derivative of f times g minus, I'm going to keep my f and multiply it by the derivative of g all over g squared. There we go. Let's clean this numerator up a little bit. Going to come on over here. Let's take a look. In the numerator, just distributing, we have 2x squared minus 2x minus x squared. Right here, 2x squared minus 2x, just checking it out, over x minus 1 squared. There we go. A little bit more work with the numerator. 2x squared minus x squared is 1x squared minus 2x over x minus 1 squared. Where does this equal 0? Just where the numerator equals 0. I don't even have to look at that denominator. So let's go ahead up a little bit. Let's factor out in x minus 2. We want to know where that equals 0. That happens where x equals 0 and x equals 2. There we go. There's where your two horizontal tangent lines would be. Let me just point out to you, point out to you that they wanted to know the points where that happened. I've run out of room. I've given you the x part of the points where it happens. You would plug each x in to get the y where it happens and give me a full point. I'm sure you're good from here. 82b, we're going to have to look in the book. So given that q of x is f of x divided by g of x, and given the chart in the book, they are asking us to find the derivative of this function at 7. We don't need the book quite yet. Let's go ahead. We're going to come down here. First of all, I'm going to write the derivative of q. Notice that it is, I'm going to use the quotient rule here. So I'm just going to write it very generically. I know what the quotient rule is. It is the derivative of f times g minus, I'm going to keep my f and multiply it by the derivative of g all over g squared. There we go. That's the derivative of q. They're telling me that x is 7. I am going to put a 7 into each one of these spots. And then we're going to go to the chart in the book and find the information that we need. Step by step. Here we go. If we could come, Bill, if we could come to this chart right here. This is the chart. They gave us f and they gave us the function g here, and they are asking us to look where x equals 7. So we're going to get each of these pieces of information for our quotient rule from here. The first thing they're asking for is the derivative of f at 7. Let's go to the function f. It's a little lighter at 7. If you notice the derivative of the function at 7, if you look at the slope of that line, that is a -1. There we go. Let's go to g of 7. Graph g. Oh, sorry, I was on graph. Gotta go back. I'm a little off to the side. Let's do the derivative of 7 again. I thought the bold line is the graph of f. G is the lighter one. No problem here. Let's go back. Let's go to 7. Notice that where x is 7, that the slope of the line of the function f is a 2. There we go. Now let's go to g of 7, now that I can see that is light colored. G of 7, they're actually asking for that function value. That is a 4. Minus f of 7 is also 4. The derivative of g at 7 is -1, right? Because I was mistaken before. And now we're going to use it. And g of 7 squared, we already got that that was a 4, and so that is 4 squared. So now, back up to the board, we got all of our information from the chart. We have some easy math here. We have 8 plus 4 is 12 over 16. I'm sure that they would reduce that to 3/4. There we go. Next, 89b. I obviously asked for A and C. They want you to prove that the derivative of cosecant is a negative cosecant cotangent. I had you memorize that fact. Why is it true? Here's what we're going to do. Where you see cosecant here, we're going to write that as 1 over sine. And let's go ahead and use the quotient rule to take the derivative here. Here's my f, here's my g. The derivative of f is 0 times g minus, I'm going to keep my f and multiply it by the derivative of g all over g squared. There we go. Notice 0 times sine is gone. I have a negative cosine over sine squared. I'm going to break this up into pieces. I'm going to call that negative cosine over sine times 1 over sine. Notice what I have here in the circle is equal to what I just wrote. I split it into pieces. Notice that negative cosine over sine is a negative cotangent. 1 over sine is cosecant. There we go. Right, we're multiplying, so I could switch these around. That's commutative, and we just proved that theorem. Number 108. Given that f of x is g of x divided by h of x, keep going back to that quotient rule, and given this information from the book, g of 2 is 3, here, these 4 pieces of information, they want you to find the derivative of f at 2. So again, here's what I'm going to do. They gave me f is g divided by h. I'm first going to write the derivative of f, right, by taking the quotient rule. Here we go. The derivative would be the derivative of g times h minus, I keep my g, multiply it by the derivative of h. Here we go, all over h squared. There we go. They're asking us to evaluate this derivative at 2. These are all 2's. And it just so happens that above they gave you all the information you need. Let's fill in all these pieces of information. The derivative of f of 2. Did they give me the derivative of g at 2? They did, right there. Did they give me h of 2? They did. Did they give me g of 2? They did, it's 3. Did they give me the derivative of h at 2? Yes, it's 4. And this is all divided by h of 2. What did we say that was? Negative 1 squared. And that final answer then, that would be a 2 minus 12, that's a 2, minus 12 all over 1, so negative 10. So they give you information in a variety of ways. 2.3c examples in purple. Number 110. It says sketch the graph of f given that f is greater than 0 for every single x, but the derivative of the function is less than 0. So that sounds like it works against each other. It says right here that the derivative of f is less than 0, meaning it's negative for all of x. That would indicate a decreasing function for any x as you go left to right, but it says that the function itself always has to be greater than 0. So for every x, meaning I can't go below the x-axis. What do? That means that there's an asymptote. This function is going to be approaching the x-axis, right? Decreasing as you go left to right, but never touching the x-axis. So a function that meets these conditions would look something like this. Notice that every y value is greater than 0, but if you drew little tangent lines, it's always decreasing. Takes a little bit of practice. Number 84. Given a right circular cylinder with a radius equal to the square root of t plus 2 and a height equal to 1/2 the square root of t, t is in seconds and units is in inches, find the rate of change of volume. That is a derivative with respect to time. You're going to start seeing this a lot. What does this mean? What's going on? What's going on is that this right circular cylinder is expanding or contracting. As time goes by, you can see these numbers are getting bigger, so it's expanding. So this right circular cylinder isn't just an object, it's growing, okay? Now, here is a silly little picture of a right circular cylinder. So the first thing we need to do before we take the derivative of the volume, we need to write the volume formula. What is the volume formula for a right circular cylinder? It's pi r squared times h. Now, notice that this makes perfect sense. It's not just a formula that comes out of nowhere. Pi r squared is circles, areas of circles, and if you run them through a height, it obviously makes a volume. It makes a circular cylinder. So we do have our volume formula now, but we do have to put in what R is and H is because they want the rate of change of volume with respect to time. Let's go ahead and do that. The volume is pi r squared. I'm going to put my R in there and square it, and my H is 1/2 the square root of t. Let's fix this up a little bit. Luckily, let's bring the constants to the front. That'll be pi over 2, right here and right here. Luckily, this square root eliminates. This one does not. So that's the square root of t times t plus 2. All right. They are asking for the rate of change of volume with respect to time. That is the derivative. We're going to write it this way. The derivative of the volume with respect to time. We call that dv dt. Let's go ahead and do that. Well, to take the derivative here, I think what I'd like to do is break it up into pieces. Watch this radical sign, students. We're going to make that 1/2. There we go. And I think what I'd like to do then, go back to dv dt in a minute, is I think I just want to do one more alteration to my volume formula. I'm going to distribute t to the 1/2 to the t. That's t to the 3/2 plus 2 plus 2t to the 1/2. There we go. I think I'd like to take the derivative this way better. Let's write that again. dv dt, derivative of the volume with respect to time. Going to keep my constant. And now I can just use the power rule instead of the product rule. So let's go ahead here. I bring my 3/2 out front and multiply it and reduce my exponent by 1. Plus, I bring my 1/2 out front, multiply it by the 2, that's a 1. And that reduces the exponent by 1. And that is t to the negative 1/2, if it's okay with you. I'm going to put that in the denominator as a positive. Now this is perfectly correct, perfectly correct. But you'll find in the book that they get a common denominator here. And so I'm going to go ahead and do that too. So let's take a look. I am going to multiply. I need a different color. There we go. The top and the bottom of this fraction by 2. The top and the bottom of this fraction by t to the 1/2. And now there's a common denominator here and here. Again, we were correct just a step ago. I doubt it would look like that answer on the AP exam or in the book. Pi over 2. I now have a common denominator of 2 t to the 1/2. If you don't mind that, I'll switch it back to radical. They do that a lot. Right here. My new numerator, t to the 1/2 times t to the 1/2 is t. That turned out pretty, plus 2. There's a couple other ways to go. The book writes it like this. You could pull that 2 out also, but we're going to say we're done and stop there. Okay, next, 130. You've never seen differential equations. You're going to see them in every section from now on. And when we get to chapter 6, we're going to be focusing on differential equations. There's a whole course in calculus at college called DiffEQs, and those are differential equations. Here's your first one. So this is kind of cool. Given that y equals 3 cosine x plus sine of x, prove the differential equation y, the second derivative of y plus y equals 0 is true. First of all, this is called a differential equation because it has derivatives in it. All we're going to do is take a look. They gave me the y. I'm going to put it right there. And what I need to do is find the second derivative of y and put it right here. Let's work that out. So the first derivative is of 3 cosine plus sine would be, bring my constant, the derivative of cosine is a negative sign, and the derivative of sine is cosine. Okay, got to take the derivative of the first derivative to get to the second one. That would be negative 3 cosine of x minus sine of x, right? Remember, the derivative of cosine is a negative sign. Let's fill in the equation. Here we go. Second derivative, negative 3 cosine of x minus sine of x, plus, let's put in y, it's right here, 3 cosine of x plus sine of x. Apparently that's supposed to equal 0. Notice it does. Negative 3 cosine of x, positive 3 cosine of x, negative sign, positive sign, 0 equals 0. We did a great job. Class, number 137, we're not going to work this whole problem out. I just know that you need a hint on one little piece here, and so I'm going to help you with that piece. They want you to write this quadratic equation, ax squared plus bx plus c, given the tangent line has a slope of 10 at the point 27. Notice I have that in quotes. I'm going to do that part with you. And the x, it has an x-intercept of 1, 0. That's going to be up to you to tackle. Here's what I want you to know right here. Most students would be really good. They would notice that the 0.27 must be on this graph because it says the tangent line has a slope at 10 at this point. So 27 must be on the graph, right? So what do we do then? I have my x is 2 and my y is 7. X is 2, y is 7. So I simply fill that out. So wherever I see an x, I'm putting in 2. I put that the function is 7. There we go. There's one equation that we can use. But what students will miss is those where it says that the slope of the tangent line is equal to 10. That means when you take the derivative of this function, that it equals 10 at this point. This is what students will miss. This is what I'm going to write here. Let's go ahead and take the derivative of this function. Please remember that a, b, and c are constants. They are not variables. So this means I'm bring my constant, and the derivative of x squared is 2x. Plus, this is a constant. The derivative of x is 1. There we go. And the derivative of c is 0. So this is the derivative. It's equal to 10 at the point 2. There we go. So again, you have a second equation to work with right here that basically says 4a plus b equals 10. We have a first equation right here to work with that we got from this point. You're going to write a third equation using that point, and then you'll have a system to solve. Good luck with that. Next, 117. We're not actually doing problem number 117. I believe that you can make good progress on that problem on your own. But on 117, it says, what can be said about the speed of an object when the velocity and acceleration have opposite signs? So you learn this in physics. We need to talk about this. Okay, so I have 4 different graphs here, and we're going to record the sign of the velocity and the acceleration, and then check the speed. So these are all distance time graphs. Distance time, distance time, distance time, distance time. This question, how is velocity and acceleration related to speed, shows up all the time on the AP exam in a couple places. Let's take a look. First of all, the velocity. That would be the rate of change of position in time on this graph. Let's draw ourselves little tangent lines. Notice that all of these slopes, or the velocity, is positive. Now let's talk about acceleration is the rate of change of velocity. Take a look at these slopes. Do you see how they're becoming more positive? The slopes are changing by becoming more positive. I just referred to the acceleration. So notice we're just going to move on to this one, and we're going to talk about the speed on each. On this graph, velocity, let's make little tangent lines to help ourselves. These are obviously positive slopes, so the velocity is positive. Let's look at how the slopes are changing. Notice they are becoming less positive, getting closer to zero. Less positive we call negative. Let's come on down to this graph. Velocity, take a look here. These slopes are definitely negative. And notice as you go to the right, they are becoming more negative. So we are going to put a negative on the acceleration too, because that's how these slopes are changing. The velocity is becoming more negative. Let's go over to this graph here, velocity. Obviously, these slopes are negative. So we're going to put a negative on the velocity. Notice though that as you go to the right, these slopes are becoming less negative. They're flattening out. We call less negative positive. Now let's look at these graphs. Notice that distance over time, that on this graph, as time increases, the distance of the object that is gaining is increasing also, so the speed is going up. Let's take a look at the speed here. As you go to the right, notice that the distance for each time unit is not increasing as fast. So it's gaining distance, but it's slowing down, so the speed is slowing down. Notice on this graph here that as time goes by, the graph is dropping faster, meaning it is losing more distance per time period. We're going to call that speed increasing. This speed over here, notice that as time goes by, it was losing distance really fast at first, and now not so much. That speed is slowing down. So notice what happens. When the signs are the same, the object is speeding up. When the signs are different, notice that the object is slowing down. And we are done with our examples for today.